right at this moment as you listen to me. Trillions of invisible particles are passing through your body at 220 kilometers per second. They've traveled through Earth, through the walls of your room, through you without touching a single atom, and you never felt a thing. Hello, it's me again. Where are you right now? In your bed, perhaps, seeking a moment of peace before sleep? Or sitting comfortably, your mind still stirred by the day's events? No matter where you are or how you feel, I'm here to accompany you on a journey that will take us from the silence of your room to the most mysterious corners of the cosmos. Before we continue, if this type of content resonates with you, consider subscribing to the channel. It's a simple way to help me keep creating these nighttime explorations of the universe's mysteries. And if you've enjoyed what you've heard so far, a like on the video makes all the difference. Now, let's discover together one of existence's best-kept secrets. Close your eyes for a moment if you can. Breathe slowly, feel the air entering and leaving your lungs. Now imagine that this same air you breathe exists in an invisible ocean of matter that permeates everything around you. This sensation of being immersed in something present but imperceptible is exactly where our journey begins. Today we're going to talk about dark matter, something that's everywhere around us, influencing every movement of the stars, every curve of galaxies, every cosmic destiny, and yet remains completely invisible to our senses. Have you ever wondered what it really means to see something? When you look at a full moon on a clear night, your eyes are capturing photons, particles of light, that traveled 384,400 kilometers through empty space just to touch your retina. Every color, every shadow, every visual detail of your life depends on this dance between light and matter. But what if I told you that most of the universe simply doesn't dance? Dark matter doesn't emit light. It doesn't reflect light. It doesn't absorb light. It exists in a realm of luminous silence that challenges our most basic understanding of reality. And yet, without it, you and I wouldn't be here. Galaxies wouldn't have formed. Stars wouldn't have been born. The cosmos itself would be a cold, empty, and storyless place. Imagine yourself walking through a forest at night. You can't see the trees around you, but you know they're there. Your feet stumble over invisible roots. The sound of your steps changes as you pass between the trunks. The wind whispers through leaves you cannot see but can definitely hear. You're navigating a world that exists beyond your vision, guided only by the clues it leaves behind. This is, poetically speaking, the situation of modern astrophysicists. They walk through a cosmos where 85% of matter is like those invisible trees, present, influential, fundamental, but completely hidden from light. And just as you would learn to navigate that nighttime forest, science has learned to map dark matter through its gravitational footprints. But before we dive into the scientific details, let me ask a question that might sound strange. Have you ever felt watched by something you couldn't see? Ever had the sensation that there was more happening around you than your senses could capture? That intuition, that feeling that there's something beyond the obvious, might be deeper than we imagine. Perhaps it's an ancestral echo of our existence in a universe where the invisible is, paradoxically, more real than the visible. Now that we've settled into this journey, let me tell you a story that forever changed our understanding of the cosmos. It was 1933, and a Swiss-American astronomer named Fritz Zwicky was observing something that shouldn't exist. He was looking at the Coma Cluster, a group of galaxies about 320 million light-years away from us, and noticed something deeply disturbing. The galaxies in this cluster were moving too fast. Imagine a group of ice skaters all spinning around a common center. For them to stay together in circular motion, there must be enough centripetal force, generated by the mass of the entire group, to keep them cohesive. But in the Coma Cluster, the galaxies were spinning so rapidly that they should have been flung into space billions of years ago. It was as if the skaters were moving so fast they should have flown off the rink, but remained mysteriously bound together. Zwicky did the calculations. The visible mass, all the stars, gas, and dust he could observe, was only a fraction of what would be needed to generate the gravity capable of keeping those galaxies in orbit. Something was missing. A lot of something. He called this invisible mass dunkel materie, dark matter. For decades, this observation was treated as a curiosity. Maybe Zwicky had made an error. Maybe there was invisible gas between the galaxies that we couldn't detect. Or maybe our understanding of gravity on cosmic scales was simply wrong. But then, 40 years later, something extraordinary happened. Vera Rubin, an American astronomer, decided to observe something apparently simpler: individual galaxies. She chose our neighbor, the Andromeda Galaxy, and began measuring how fast its stars orbited the galactic center. What she expected to find was a familiar pattern, like our solar system, where planets farther from the sun move slower than those closer in. But that's not what she found. Stars at the galaxy's edges were moving almost as fast as those at the center. It was as if you discovered that Neptune travels through its orbit at the same speed as Mercury. Something was sustaining those distant stars, something that exerted gravitational influence but remained completely invisible. Have you ever tried to balance on a wooden plank suspended only by its ends? Without support in the middle, it would be impossible. But that was exactly what galaxies were doing, maintaining balance and spinning uniformly as if there were invisible support distributed throughout their extent. Rubin had discovered what we now call flat rotation curves, a phenomenon that only made sense if each galaxy was immersed in a gigantic halo of invisible matter, 5 times more massive than all the visible matter combined. Imagine your house surrounded by an invisible sphere the size of a city block, exerting influence over everything inside, but without you ever being able to see, touch, or directly detect it. Rubin's discovery was the second great pillar of evidence for dark matter. First Zwicky with clusters, then Rubin with individual galaxies. But nature is stubborn and scientists are professionally skeptical. More evidence was needed, more footprints of this cosmic ghost, and they came. Oh, how they came! In the following years, increasingly sophisticated observations revealed that dark matter wasn't just a convenient hypothesis, it was an absolute necessity to explain the universe's structure. Without it, the first galaxies would never have formed after the Big Bang. Without it, the cosmic background radiation would have a completely different pattern. Without it, we wouldn't be here. But perhaps the most spectacular evidence came from an unexpected source: light itself. You know that gravity can bend space, right? Einstein taught us that massive objects deform the fabric of spacetime like a bowling ball on an elastic bed. And when light passes through these deformed regions, it follows the curves, a phenomenon called gravitational lensing. Astronomers discovered they could use this effect as a cosmic magnifying glass. Distant galaxies, curved and distorted by the gravity of invisible structures, revealed the location and amount of dark matter with impressive precision. It was as if we could finally see the ghost's footprints in the cosmic sand. Have you ever thought about how peculiar it is that we can detect something through its absence? Dark matter is like a hole in reality, defined not by what it is, but by what we can't see. And yet, its footprints are everywhere, whispering secrets about the true nature of the cosmos. Breathe deeply with me for a moment. Feel the air filling your lungs, expanding your chest, nourishing every cell in your body. Now imagine that between each oxygen molecule you just inhaled, there are trillions of dark matter particles silently passing through your body. Your room, our entire Earth, without leaving the slightest trace of their passage. They're there now, as I speak, and you listen, flowing through us like ghosts in a perpetual cosmic dance. This is the invisible reality we live in. And to map this reality, scientists had to become detectives of a very particular kind, detectives investigating crimes without scenes, suspects without bodies, evidence that can only be perceived through its consequences. The first great map of dark matter came from an accidental discovery that would forever change our understanding of the universe. In 1965, 2 Bell Labs engineers, Arno Penzias and Robert Wilson, were calibrating a microwave antenna when they encountered a strange noise they couldn't eliminate. It was a faint, constant whisper coming from all directions in the sky. They cleaned the antenna, removed pigeon nests, adjusted equipment, but the signal persisted. What they had discovered, without knowing it, was the echo of the Big Bang itself, the cosmic microwave background radiation. Imagine the universe as a giant bell that was struck 13.8 billion years ago. That ring still resonates through the cosmos, and we can hear it with sufficiently sensitive antennas. But even more fascinating, the small variations in this radiation, almost imperceptible temperature fluctuations, carry imprinted the seeds of all future cosmic structure. Think of these fluctuations as ripples in a perfectly calm lake. Where the water is slightly higher, eventually larger waves will form. Where it's lower, valleys will be established. In the primordial universe, where the radiation was slightly more intense, matter, including dark matter, began to concentrate. Where it was less intense, cosmic voids formed. But here's the crucial detail. The fluctuations we observe in the cosmic background radiation only make sense if we include dark matter in the equation. Without it, the gravitational seeds would be too weak to grow and become the galaxies and clusters we see today. Dark matter acted as an invisible scaffolding, providing the structure upon which ordinary matter could condense and form the first stars. In the following decades, space missions like COBE, WMAP, and Planck mapped this radiation with increasing precision. The result was a map of the baby universe, a photograph taken when the cosmos was only 380,000 years old. And this map revealed something extraordinary. 26.8% of the universe is dark matter, while only 9% is ordinary matter, the protons, neutrons, and electrons were made of. Can you imagine that? In a cosmic meeting of 100 people, only 5 would be made of the same substance as you. About 27 would be made of dark matter, present, influential, but completely invisible, and the rest? Well, that's another equally mysterious story called dark energy, but that's a journey for another time. Modern cosmologists have created computer simulations that reproduce the universe's evolution from its first moments to today. These simulations are like digital time machines, allowing us to observe the formation of the first cosmic structures. And they show us something poetic. Dark matter forms a cosmic web. Giant filaments of invisible matter connecting galaxy clusters like a cosmic neural network. Imagine the universe as a giant three-dimensional sponge. The sponge's walls are made of dark matter, concentrated in filaments that stretch for hundreds of millions of light years. At the points where these filaments intersect, gravity is more intense, and that's where galaxies are born, like bright beads strung on the nodes of an invisible network. This structure isn't just beautiful, it's fundamental. Without the cosmic web of dark matter, the universe would be a uniform, featureless place, incapable of generating the complexity necessary for star formation, planets, and eventually, life. We are literally products of the universe's invisible architecture. But perhaps most impressive is realizing that this discovery represents a revolution as profound as Copernicus's or Darwin's. Copernicus removed us from the spatial center of the universe. Darwin removed us from the biological center of creation. And now we discover that we're not even made of the cosmos's main substance. We are a cosmic minority, surfing on the gravitational waves of an invisible ocean. And yet, here we are, capable of thinking, feeling, questioning, and discovering our own relative irrelevance. Isn't that profoundly beautiful? Isn't that reason for both humility and wonder at the same time? Now that we understand where dark matter is and how much of it exists, we come to the most fundamental question of all. What is it made of? This is where our journey becomes truly surreal, because we're about to explore a realm of physics where common intuition simply doesn't work. Close your eyes and imagine you're holding a rock in your hand. You feel its weight, its texture, its temperature. This rock is made of atoms, protons, neutrons, and electrons dancing in an electromagnetic symphony. Electrons orbit atomic nuclei because they're attracted by the electromagnetic force. It's this same force that allows your fingers to feel the rock, your retina to capture the light reflected by it, for it to interact with the world in detectable ways. But what if there were particles that simply ignored this force? Particles that would pass through the rock, your hand, your body, our entire planet as if nothing existed? Particles that only interacted through gravity, the weakest of the 4 fundamental forces? Welcome to the strange world of WIMPs, weakly interacting massive particles. This is one of the main candidates to explain dark matter, and they represent one of the most elegant and disturbing ideas in modern physics. Imagine you're at a crowded party, trying to cross through a crowd. As ordinary matter, you bump into people, need to say, "Excuse me," navigate around conversation groups. Your passage through the party is marked by constant interactions. But WIMPs would be like ghosts at that same party, passing through people without touching them, without being seen, without leaving a trace, but still exerting a subtle gravitational influence on the movement of the entire crowd. The theoretical beauty of WIMPs lies in their simplicity. They would solve not just the mystery of dark matter, but also connect two apparently unrelated problems in physics: the need for invisible matter in the cosmos and the gaps in our standard model of elementary particles. Did you know we live constantly bombarded by particles that pass through our bodies without us noticing? Neutrinos, nearly massless particles produced in the sun's core and other nuclear reactions, pass through Earth like bullets through a vapor cloud. Trillions of them pass through you every second and you never feel anything. They're like cosmic whispers that can only be heard with extraordinarily sensitive detectors. WIMPs would be similar to neutrinos, but much heavier, perhaps 100 times more massive than a proton. And here's the almost magical aspect. If they exist, they're everywhere around us. Right at this moment, as you listen to me, millions of dark matter particles could be passing through every cubic centimeter of space around you. But there's another equally fascinating candidate: axions. Imagine particles so light they're almost pure energy, so weakly interacting that billions of them could dance on the head of a pin without the pin knowing they're there. Axions were originally proposed to solve a completely different problem in nuclear physics, but scientists realized they could also explain dark matter. The primordial universe would have produced axions in astronomical quantities, and they would still be around, an invisible sea of ultralight particles permeating the entire cosmos. It's as if the universe were an invisible ocean and everything we know, galaxies, stars, planets, you and I were just foam on the surface. There's yet a third possibility that challenges our understanding of reality: sterile dark matter. Imagine particles that are like cosmic hermits. They interact so weakly with everything else that they could be present in enormous quantities without ever revealing themselves. They would be produced in processes we don't yet fully understand, perhaps involving extra dimensions of space-time that our current physics only glimpses. Each of these possibilities requires extraordinary experiments to be tested. Laboratories buried kilometers underground to protect from cosmic radiation. Detectors cooled to temperatures near absolute zero to capture the most subtle interactions. Particle accelerators the size of entire cities trying to recreate the conditions of the primordial universe. It's an almost spiritual quest, scientists dedicating entire lives to detecting particles that, by definition, don't want to be detected. It's like trying to hear the softest whisper amid the roar of a waterfall. And yet they persevere, because they know that finding dark matter would be one of the greatest discoveries in human history. Have you ever stopped to think how extraordinary this is? We're trying to detect something that represents 85% of the universe's matter, but interacts so weakly with us that it can pass through the entire Earth without touching a single atom. It's like trying to catch snowflakes with a fishing net. In the quietude of night, while you rest, there's a hunt happening, not in Earth's forests or savannas, but in the world's most advanced laboratories, where scientists dedicate their lives to capturing prey that may never be captured. They are the dark matter hunters, and their traps are some of the most sophisticated constructions ever created by humanity. Imagine descending in an elevator that plunges 1.5 miles below Earth's surface, passing through rock layers that formed over millions of years. The air becomes denser, the silence deeper. Finally, you arrive at the Gran Sasso National Laboratory in Italy, buried under the mountain like an underground cathedral dedicated to the search for the invisible. Why go so deep? Because every second, trillions of particles from space bombard our atmosphere, cosmic rays that would create constant noise in any sensitive detector. But solid rock acts as a cosmic filter, blocking almost everything. Except theoretically dark matter particles. They would pass through the entire mountain as if it were made of air. In the heart of this underground laboratory, scientists have built detectors that are true works of technological art. Xenon 1T, for example, is a cylindrical tank containing a ton of ultra-pure liquid xenon, cooled to -95 degrees Celsius and protected by layers upon layers of shielding. The xenon is so pure it's considered the cleanest liquid ever created by humanity, cleaner than any water, purer than any substance you could imagine. Why this extreme purity? Because scientists are looking for an event so rare it might happen only once every few years, even with billions of dark matter particles constantly passing through the detector. It's like looking for a single drop of ink in a perfectly crystalline ocean. The theory is elegant in its simplicity. When a dark matter particle finally collides with a xenon nucleus, a statistically inevitable but extraordinarily rare event, it will transfer a tiny amount of energy. The struck nucleus will recoil like a billiard ball, creating a microscopic flash of light and releasing free electrons. Ultra-sensitive sensors would detect both the light and the electrons, recording the signature of this cosmic collision. But imagine the patience required. Years of observation, filtering every signal, discarding billions of events caused by natural radiation, seismic vibrations, cosmic rays that manage to penetrate the shielding. It's like being a technological monk, meditating with machines that took decades to build, waiting for a whisper that may never come. On the other side of the world, at Canada's Snow Lab, 2 kilometers below the surface, other hunters employ different strategies. The PICO experiment uses glass flasks containing superheated fluids, liquids maintained at temperatures above their normal boiling point, but prevented from boiling by carefully controlled pressure. A single dark matter particle colliding with a molecule would be enough to create a tiny vapor bubble, which would be detected by ultra-fast cameras. It's almost poetic, scientists trying to capture the invisible through bubbles that last milliseconds, like trying to photograph thoughts or weigh dreams. There are also completely different approaches. In space, the Fermi telescope searches for signs of dark matter annihilation, the hypothesis that when 2 dark matter particles meet, they destroy each other, releasing bursts of gamma radiation. It's like looking for silent fireworks exploding in places where there should be nothing. And then there are directional experiments, trying to detect not just dark matter's collision, but also the direction it came from. As our solar system moves through the galaxy at 220 kilometers per second, we should feel a wind of dark matter coming from the direction of our movement, like feeling a breeze when you run, even on a windless day. Directional detectors use special gases where particles leave microscopic trails like vapor tracks in a cloud chamber. If we could detect this dark matter wind, it would be spectacular confirmation that we're truly immersed in an ocean of invisible particles. But perhaps most impressive is the scale of international cooperation required. Physicists from around the world sharing data, techniques, frustrations, and hopes. It's as if all humanity had united around a fundamental question: what is the universe made of? And even if decades pass without direct detection, each negative experiment teaches us something. Each non-discovery eliminates possibilities, refines theories, brings us closer to the answer. It's a form of science that requires almost spiritual patience, a faith in the importance of the question that goes beyond immediate results. Have you ever thought about what it means to dedicate an entire life to searching for something that may not exist as we imagine it? These scientists are explorers of a very particular kind, navigating not through oceans or continents, but through the very fabric of reality. There's a place on the border between France and Switzerland where humanity built the most complex machine ever created, a ring 27 kilometers in circumference, buried 100 meters underground, where protons are accelerated to 99.9999991% the speed of light before colliding with energy that recreates, for microscopic fractions of a second, the conditions that existed trillionths of a second after the Big Bang. This is the Large Hadron Collider, the LHC, and it represents our most ambitious attempt to produce dark matter in the laboratory. If we can't capture these ghost particles as they pass through our underground detectors, perhaps we can create them from scratch, forge them in the most intense energy furnace ever built by humanity. Imagine 2 proton beams, each containing 100 billion particles, spinning in opposite directions through this circular tunnel. They travel in a vacuum more perfect than interstellar space, guided by superconducting magnets cooled to minus 271 degrees Celsius, colder than deep space. When these beams finally meet at 4 collision points around the ring, Each encounter releases enough energy to create particles that haven't existed since the universe's first moments. It's in these collisions that physicists hope to find direct evidence of dark matter. The theory of supersymmetry, an elegant extension of the standard model of particle physics, predicts that every known particle should have a supersymmetric partner. The electron's partner would be the selectron, the quarks would be the squark, the neutrinos would be the sneutrino, and the lightest, most stable supersymmetric particle would be a perfect candidate for dark matter. When protons collide in the LHC with colossal energies, these supersymmetric particles could be created in pairs. But since they interact weakly with ordinary matter, they would escape the detectors without leaving a direct trace. How then would we know they were created? Here enters one of experimental physics' most elegant ideas: conservation of energy and momentum. Imagine two ice skaters pushing off each other and moving away in opposite directions. If you saw only one skater moving away, you'd immediately know there must be another moving in the opposite direction, even if you couldn't see it. In the LHC, when energy and momentum systematically disappear from collisions, this could be the signature of invisible dark matter particle creation. The LHC's detectors are technological cathedrals. Atlas, for example, is 25 meters tall, 45 meters long, and weighs 7,000 tons. It's like a giant cosmic eye, with concentric layers of sensors capable of tracking particles that exist for billionths of a second and travel distances smaller than a hair's diameter. Each collision produces hundreds of secondary particles, creating a cascade of events that must be reconstructed like a three-dimensional puzzle in real time. Computers analyze 40 million collisions per second, looking for anomalous patterns, energy signatures, and visible footprints that could reveal dark matter's presence. It's a search that combines clockwork precision with the energy of nuclear explosions. And yet, after more than a decade of operation, the LHC hasn't found direct evidence of dark matter. Each negative result is simultaneously a disappointment and a step forward, eliminating possibilities, refining theories, forcing physicists to think more creatively about reality's nature. But perhaps the most impressive thing about the LHC is what it represents as a human enterprise. Thousands of scientists from dozens of countries working together for decades, investing billions of dollars in a fundamental question: what is the universe made of? It's as if our species had collectively decided that some questions are too important to remain unanswered. And even if the LHC never directly detects dark matter, it has already taught us profound lessons. The discovery of the Higgs boson in 2012, the particle that gives mass to all other particles, was a triumph of theoretical physics that took almost 50 years to be experimentally confirmed. It showed us that even at the most fundamental scales, the universe is stranger and more wonderful than we imagined. There are proposals to build even larger colliders, rings of 100 kilometers or more, capable of probing energies that would bring us even closer to Big Bang conditions. Imagine a project that would encircle an entire city, a machine so large it would be visible from space, dedicated entirely to searching for the cosmos's most elusive particles. Have you ever wondered what this says about us as a species? That we're willing to move mountains, literally, to answer questions that have no immediate practical application? That we build technological temples dedicated to pure curiosity? There's something profoundly beautiful in this, and perhaps it's exactly this capacity to ask questions, bigger than ourselves, that defines us as human beings. While physicists dig tunnels and build accelerators on Earth, the universe offers natural laboratories on a scale we could never replicate. Entire galaxies collide in cosmic slow motion, releasing energies trillions of times greater than any human machine. Stars explode in supernovas, creating temperature and pressure conditions that transform the very elements. And in these cataclysmic phenomena, dark matter leaves its clearest footprints. Imagine two galaxies approaching each other over billions of years, their enormous dark matter halos beginning to interact gravitationally long before their stars meet. It's like two invisible clouds colliding in space, and we only perceive the event through the effects on the small visible raindrops, the stars they carry. The Bullet Cluster is perhaps the most spectacular example of this phenomenon. Two galaxy clusters collided about 150 million years ago, creating one of the most convincing pieces of evidence for dark matter's existence. What makes this collision so revealing is that it dramatically separated ordinary matter from dark matter. During the collision, the heated intergalactic gas, most of the visible matter in clusters, was slowed by friction and remained at the collision center, glowing intensely in X-rays like a cosmic forge. But dark matter, which only interacts gravitationally, passed through the collision almost unaffected, like two groups of ghosts passing through each other. Using gravitational lensing, astronomers mapped where the total mass is concentrated in the system, and they discovered something extraordinary. Most of the mass was separated from the visible matter, moving ahead of the bright gases as if it had passed through the collision intact. It was dark matter, finally caught in action. It's as if you watched two bee swarms collide, but the bees got trapped in the middle while their shadows continued flying forward. The bullet cluster showed us that dark matter is real, separable from ordinary matter, and behaves exactly as theories predicted. But the universe offers even more extreme laboratories. Consider white dwarfs, dead stars so dense that a teaspoon of their material would weigh as much as an elephant. When a white dwarf accumulates enough matter from a companion star, it explodes in a Type Ia supernova, releasing for a few weeks more energy than our Sun will produce in its entire 10 billion-year lifetime. These explosions are so uniform they serve as cosmic standard candles. Their properties are so consistent, we can use them to measure distances across the universe. And it was by studying distant supernovas that astronomers made a discovery that shook cosmology's foundations. The universe isn't just expanding, it's accelerating. This acceleration requires a repulsive force distributed throughout all space, something we call dark energy. And here our journey becomes even more mysterious, because we discovered we live in a universe dominated not just by invisible matter, but also by an even stranger form of energy. If dark matter is the invisible scaffolding upon which cosmic structure is built, dark energy is the force slowly tearing that structure apart, pushing galaxies ever farther from each other. It's as if space itself were a compressed spring, constantly expanding and creating more space between itself. Pulsars, neutron stars that spin hundreds of times per second, emitting radiation beams like cosmic lighthouses, also serve as laboratories for testing dark matter. These objects are so dense that a teaspoon of their matter would weigh as much as a mountain. If axions existed, they would be produced in the intense magnetic fields around pulsars and could be detected through their subtle effects on the radiation we observe. There are also so-called compact dark objects, primordial black holes that could have formed in the early universe. If a significant fraction of dark matter were composed of these mini black holes, they would act as microscopic gravitational lenses, causing detectable variations in the brightness of distant stars as they passed in front of them. Each of these natural phenomena offers a unique window for investigating dark matter. It's as if the universe were an infinitely large experimental laboratory, conducting experiments that would last billions of years and that we could never perform on Earth. And we, small observers on a rocky planet around an average star, have the extraordinary privilege of being conscious witnesses to these cosmic experiments. Have you ever stopped to think about our unique position in the cosmos? We're made of ordinary matter, a cosmic minority, but we're apparently the only ones capable of contemplating and trying to understand the dark matter that dominates everything around us. It's as if the universe had developed eyes to observe itself, and those eyes were us. Amid the scientific consensus about dark matter, there are dissenting voices, courageous scientists who propose an even more radical possibility. What if we didn't need invisible matter? What if, instead, our understanding of gravity itself were incomplete? Imagine discovering that the physics laws we learned in school, tested and confirmed countless times in terrestrial laboratories, simply don't apply on vast cosmic scales. It's a possibility that's simultaneously exciting and disturbing, like discovering that mathematics rules change when you count very large numbers. The most prominent theory in this category is called modified Newtonian dynamics. Proposed by Israeli physicist Mordechai Milgram in the 1980s, it suggests that Newton's law of gravity, which worked perfectly for describing planetary motions and rocket launches, needs to be modified when dealing with extremely small accelerations. Think of gravity as you've always known it, the force between Two objects is proportional to their masses and inversely proportional to the square of the distance between them. It's an elegant, simple, universal law. But Mom proposes that when gravitational accelerations become very small, as at galaxies' outer edges, gravity behaves slightly differently, becoming stronger than Newton predicted. It's a subtle change, almost imperceptible on human scales, but becomes dramatically important on galactic scales. With this modification, stars at galaxies' edges would naturally orbit faster than Newtonian gravity predicts, exactly what Vera Rubin observed, without needing to invoke invisible matter. Mohandi's elegance lies in its simplicity. With a single modification to gravity's law, it explains galactic rotation curves, galaxy cluster dynamics, and many other observations we attribute to dark matter. It's like discovering that a complex puzzle can be solved not by adding invisible pieces, but by slightly redesigning the pieces we already have. But Mont faces serious challenges. It works well for individual galaxies, but has difficulties explaining larger structures like galaxy clusters. And mainly, it can't explain the fluctuations in cosmic background radiation, those primordial footprints that seem to require dark matter to make sense. There are even more exotic theories. Entropic gravity, proposed by Dutch physicist Erik Verlinde, suggests that gravity isn't a fundamental force, but an emergent phenomenon like temperature or pressure arising from more fundamental properties of spacetime. In this view, what we call dark matter would actually be a manifestation of how information is stored in spacetime structure. Imagine spacetime as a quantum ocean, where each point contains information about the universe's state. Gravity would emerge from this information ocean's tendency to equilibrate, like water flowing from high places to low. The footprints we attribute to dark matter would actually be information flow patterns in this cosmic ocean. There are also theories proposing extra dimensions of space. Our daily experience familiarizes us with three spatial dimensions: height, width, and depth. But some physical theories suggest there could be additional dimensions, compacted on scales so small we don't perceive them directly. Dark matter could be ordinary matter leaking from these extra dimensions, exerting gravitational influence in our familiar three-dimensional space. It's like imagining we live on a sheet of paper's surface, but there's a three-dimensional world around us that we can only perceive through shadows projected on our two-dimensional surface. Dark matter would be the shadow of objects in dimensions we can't see directly. Some of the most speculative theories propose that dark matter could be made of mirror matter, an exact copy of all ordinary matter, but interacting through different forces. There would be mirror stars, mirror planets, perhaps even mirror life, existing parallel to our universe, but only detectable through gravity. Another fascinating possibility is that dark matter is composed of Q-balls, stable quantum structures made of scalar fields. These exotic objects could form in the early universe and persist until today, behaving like dark matter particles on large scales but having rich, complex internal structure. What all these alternative theories share is a willingness to question fundamental assumptions. They remind us that science progresses not just through confirming existing theories, but also through the courage to imagine that our current understanding might be incomplete. And perhaps that's the most profound lesson. In a universe where 95% of the content is mysterious, intellectual humility might be our most important tool. We don't know if dark matter is made of exotic particles, represents a modification of gravity, or is something completely different we haven't even imagined yet. What we do know is that the cosmos is trying to teach us something fundamental about reality's nature. And that lesson might be even stranger and more wonderful than anything we've managed to imagine so far. There's a particular melancholy in experimental science when years of dedicated work produce only silence. Underground detectors continue their patient vigil, recording millions of events, filtering countless false signals, but so far haven't captured a single unequivocal dark matter particle. It's a silence that speaks volumes. Imagine being a birdwatcher who spent decades in the forest, listening intently, waiting for the song of a species that may or may not exist. Every noise, every movement in the vegetation sparks hope, but invariably turns out to be something common, a squirrel, a falling leaf, the wind. And yet you keep listening because you know that if this species exists, Hearing it would be the discovery of a lifetime. This is how physicists who have dedicated entire careers to direct dark matter detection feel. Each experiment that fails to find a definitive signal is simultaneously a disappointment and valuable information. The universe is telling us something, even if it's not quite how you think. The Xenon-1T detector, after years of operation, established the most rigorous limits ever achieved on WIMP properties. If they exist, they interact with ordinary matter even more weakly than the most optimistic theories predicted. It's like discovering that the ghosts you're hunting are even more ethereal than you imagined. Successive detectors have become increasingly sensitive. LUX-Zeppelin, Xenon's successor, can detect recoil events so subtle they're like feeling a single raindrop in a football stadium during a storm. And yet, the silence persists. This doesn't necessarily mean WIMPs don't exist. Perhaps they interact even more weakly than predicted. Perhaps they only exist in certain regions of parameter space we haven't fully explored yet. Or perhaps they're so different from what we imagine that our current detectors are like trying to hear music by looking through a microscope. There's also the possibility that we've already detected dark matter but don't recognize the signals. Several experiments have reported intriguing anomalies over the years, small excesses of events they can't fully explain. The Dama Libra detector in Italy has consistently reported an annual modulation in its event rate that could be caused by Earth's movement through a dark matter wind. Imagine our orbital journey around the Sun as a car trip through an invisible cosmic snowstorm. When we travel in the storm's direction, more flakes should hit our windshield. When we travel in the opposite direction, fewer flakes. The Dama signal could be this seasonal modulation in dark matter wind intensity. But other experiments using different technologies haven't been able to confirm the Dama signal. And so we have one of experimental physics' most frustratingly persistent mysteries, a signal that might be dark matter, but could also be a subtle systematic effect we don't fully understand. The detector's silence has forced theorists to become increasingly creative. Perhaps dark matter isn't made of a single particle species, but of an entire dark sector, a zoo of invisible particles interacting through their own dark forces. It would be like discovering there are not just invisible animals, but entire ecosystems operating parallel to our visible world. Or perhaps dark matter particles are so light that current detectors optimized for heavy WIMPs simply can't see them. It would be like trying to catch butterflies with a fishing net. You need completely different tools for completely different prey. Future experiments are being designed to probe completely new regimes of mass and interaction. Axion detectors will use intense magnetic fields to convert these hypothetical ultralight particles into detectable photons. It's like trying to hear whispers by converting them into shouts through extremely sensitive amplifiers. There are also proposals for detectors the size of skyscrapers, with target material volumes thousands of times larger than current experiments. If dark matter interacts even more weakly than we think, perhaps we simply need much larger targets to have any chance of capturing a particle. But perhaps the detector's silence teaches us the most profound lesson about the nature of scientific discovery itself. The absence of an expected signal is, in itself, a form of knowledge. Each null experiment teaches us that the universe is more subtle, more complex, more surprising than our initial theories suggested. And there's an almost Zen beauty in these experiments' patience. Machines built to function for decades, scientists dedicating entire careers to questions that may not have simple answers. Humanity as a whole investing enormous resources in the search for fundamental knowledge without guarantee of practical return. This is what makes us human, isn't it? This capacity to ask questions bigger than ourselves, to build cathedrals of knowledge that may take generations to complete. The detector's silence isn't a failure, it's part of the longer conversation our species is having with the cosmos. To truly understand dark matter, we need to travel not just through space, but through time, returning to the first moments after the Big Bang, when the universe was simpler, hotter, and when the seeds of all future structure were planted in a cosmos that could fit in the palm of a hand. Breathe slowly and try to imagine the beginning of everything. Not a place because there were no places. Not a specific moment because time itself was being born. 13. 8 billion years ago. All the matter and energy that compose the billions of observable galaxies were compressed into a volume smaller than a proton, at temperatures and densities that defy any terrestrial analogy. In the first trillionths of a second, a period so brief that light couldn't traverse even an atomic nucleus, the universe underwent explosive inflationary expansion. Space-time stretched faster than the speed of light, carrying regions that had been in thermal contact to such vast distances they would never communicate again. It's during this inflationary epoch that microscopic quantum fluctuations, fundamental uncertainties in spacetime's fabric, were stretched to cosmic scales, becoming the seeds of all future structures. Imagine quantum ripples smaller than a proton being inflated to galaxy size, carrying with them the patterns that would eventually become galaxy clusters, cosmic voids, and all the universe's architecture. But here's the crucial detail. These primordial fluctuations only make sense if we include dark matter in the story. Without it, the gravitational seeds would be too weak to grow against the universe's expansion. Dark matter acted as the cosmos's first structural agent, providing the gravitational scaffolding upon which ordinary matter could later condense. As the universe cooled and expanded, it went through a series of phase transitions, critical moments, where the laws of physics assumed their modern forms. First, the four fundamental forces separated from a single unified force. Then, elementary particles acquired mass. Around 1 second after the Big Bang, protons and neutrons formed. In the first 20 minutes, primordial nucleosynthesis forged the nuclei of hydrogen, helium, and lithium. Throughout this entire period, dark matter remained as a silent presence, interacting gravitationally with ordinary matter but following its own separate evolution. If it was composed of WIMPs, they would have been created in abundance in the first moments, when energies were high enough to produce these exotic particles. As the universe cooled, WIMP production ceased, and they began annihilating each other until only a residual amount remained. Exactly the amount needed to explain the dark matter we observe today. It's a story of perfect cosmic timing. If WIMPs interacted slightly more strongly, they would have annihilated completely, leaving no traces. If they interacted slightly more weakly, there would be too much dark matter, and the universe would have gravitationally collapsed before stars could form. This delicate balance is known as the WIMP miracle, a cosmic coincidence that seems precisely tuned to allow our existence. For about 380,000 years after the Big Bang, the universe remained opaque to light. Free electrons constantly scattered photons, creating an impenetrable cosmic fog. But then, as temperatures dropped sufficiently, electrons and nuclei combined to form the first neutral atoms. This epoch, called recombination, free photons to travel through space, and it's these ancient photons we detect today as the cosmic background radiation. Dark matter, however, didn't participate in recombination. It remained invisible to radiation, continuing to gravitationally collapse and form the universe's first structures. When ordinary matter finally could condense after radiation stopped keeping it dispersed through pressure, it found dark matter halos already waiting, like invisible foundations upon which the first stars and galaxies could form. Modern computer simulations can reproduce this cosmic history in impressive detail. Starting with the primordial fluctuations measured in the cosmic background radiation, they evolved dark and ordinary matter through 8 billion years of cosmic history, producing simulated universes that look remarkably like what we observe. These simulations reveal that dark matter forms a hierarchy of structures. Small halos merge to form larger halos, which merge to form even larger structures in a process that continues today. It's like watching the construction of a cosmic city in ultra-slow motion, where the invisible foundations are laid first and the bright buildings, the galaxies, are built upon them. But perhaps the most poetic aspect of this story is realizing that you and I are made of matter with a 13.8 billion year history. Every atom in your body was forged in a star's core that lived and died before the sun was born. And that star could only exist because dark matter created the gravitational conditions necessary for its formation. We are literally children of the stars and stepchildren of dark matter. Our existence depends as much on what we can see as on what remains forever invisible. Isn't that profoundly humbling and wonderful at the same time? As our journey approaches its end, it's time to look not just to the past, but to the future, both the future of dark matter research and the future of the universe itself. And here, in the contemplative quietude of this night, we can glimpse not just where science will take us, but what will be the final destiny of the cosmos we share with these invisible particles. The coming years promise a revolution in astronomy. The James Webb Space Telescope, already operational, is probing the first galaxies that formed when the universe was only a few 100 million years old. These observations will show us how dark matter sculpted the first cosmic structures, revealing details about epochs we've never been able to observe directly. Imagine looking at photographs of your childhood, but this time seeing not just you, but also the invisible influences that shaped who you would become. Webb is doing exactly this with the universe, revealing how dark matter halos guided the formation of the first stars and galaxies. The LSST Legacy Survey of Space and Time project, which will begin operating in Chile, will map billions of galaxies over a decade, creating the most detailed map ever made of dark matter distribution in the cosmos. It will be like creating a three-dimensional atlas of the invisible, revealing the cosmic web in unprecedented detail. Next-generation detectors like Darwin and ORIS will be built with liquid xenon volumes up to 100 times larger than current experiments. If WIMPs exist and interact even weakly with ordinary matter, these giant detectors should finally capture some of them. It will be like replacing a fishing net with a lake-sized net. There are also proposals for space experiments that would search for dark matter, using techniques impossible on Earth. Orbital telescopes could search for dark matter annihilation signals in the galaxy's center, where it should be most concentrated. Deep space detectors could map the dark matter wind with precision impossible to achieve on our geologically active planet. But perhaps the most exciting developments will come from completely unexpected directions. Quantum computing may revolutionize our ability to simulate dark matter physics. Artificial intelligence algorithms are already being used to search for subtle patterns in astronomical data that escape human attention. New theories of quantum gravity may reveal connections between dark matter and spacetime's fundamental nature. And if we never directly detect dark matter, that too would be a profound discovery. It would mean it's even stranger than we imagine, or that our understanding of gravity needs fundamental revision. Either of these possibilities would represent a revolution in our understanding of reality. Now, let me take you on a journey through cosmic time to glimpse the final destiny of the universe we inhabit. In a few billion years, our galaxy will collide with Andromeda in a slow, majestic gravitational dance. The dark matter halos of both galaxies will merge, creating an even larger structure, while their stars are rearranged like particles of cosmic dust. During this process, dark matter will remain as it always has, invisible, silent, but fundamental. It will guide the galaxy's merger through its gravitational influence, shaping the destiny of trillions of stars without ever revealing itself directly to any hypothetical observer who might witness the event. On even longer timescales, trillions upon trillions of years, stars themselves will stop being born as the universe exhausts its hydrogen supply. One by one, they will die, leaving behind white dwarfs, neutron stars, and black holes. Even so, dark matter will persist, an eternal presence in a cosmos that becomes increasingly cold and dark. If dark matter is composed of particles that can annihilate each other, it will gradually diminish over countless eons. Occasionally, two particles will meet in the frozen void of intergalactic space and destroy each other in a flash of energy, perhaps the last fireworks of a dying universe. Eventually, even black holes will evaporate through Hawking radiation, a process so slow that a black hole with the sun's mass would take longer to evaporate than the current universe's age raised to the 67th power. But even after the last black hole disintegrates, dark matter may still be there, silent witness to a cosmos that has reached the end of its story. Or perhaps we'll discover that dark matter is absolutely stable, persisting forever in a universe that has expanded so much that each particle is isolated from others by distances larger than entire galaxies. It would be a final cosmic solitude, invisible particles floating alone through space that has become so vast and empty that nothing more can happen. But there are also more optimistic possibilities. If future civilizations fully understand dark matter's nature, perhaps they can use it in ways we can't even imagine. Perhaps it will become an energy source or a means of communication across cosmic distances, or even a way to travel between stars in ways that defy our current physics. Imagine civilizations that learn to see dark matter directly, for whom the invisible universe is as real and detailed as the visible cosmos is for us. To these beings, our blindness to dark matter would seem as limiting as the inability to see colors would seem to us. Perhaps we'll discover that dark matter isn't just passive matter, but possesses complex properties and structures we don't even suspect yet. Perhaps there are dark atoms, dark molecules, maybe even dark life, forms of complex organization happening in the universe's dark sector, completely parallel and invisible to everything we know. It would be the ultimate discovery that we're not just surrounded by invisible matter, but by an invisible biosphere, an entire cosmic ecology operating according to its own rules on its own timescales, pursuing its own evolutionary purposes. And if this is true, then our search for dark matter isn't just a scientific question, but a search for our cosmic neighbors, beings who may have been beside us throughout all of human history, but in a realm we never learned to perceive. Now, in the deep quietude of this night, let me ask a question that goes beyond science. What does it mean to live in a universe where most of reality is invisible? How does this change our understanding not just of the cosmos, but of ourselves and our place in existence? The discovery of dark matter represents more than a scientific revolution. It's a philosophical revolution that forces us to reconsider fundamental concepts like reality, knowledge, and perception. For millennia, our understanding of the world was shaped by what we could see, touch, measure directly. Seeing is believing wasn't just a popular saying, but the epistemological foundation of our civilization. But dark matter teaches us that reality is much vaster than our perception. It's like discovering you've spent your entire life in a room lit only by a candle, believing that what you could see was all that existed, only to realize you're surrounded by an immense palace shrouded in darkness. Think of ancient philosophers who contemplated reality's fundamental nature. Plato with his cave allegory, where prisoners mistake shadows on the wall for all of reality. Kant with his distinction between the phenomenal world, what we can experience, and the noumenal world, the thing in itself, forever beyond our direct perception. Dark matter is, in a way, Kant's noumenal world made literal. It exists, influences our reality in fundamental ways, but remains forever beyond our direct perception. We can't see it, touch it, or detect it through any conventional means. And yet, without it, we wouldn't exist. This leads us to profound questions about the nature of knowledge. If most of the universe is invisible to us, what else are we missing? How many layers of reality remain hidden, not because they're fundamentally unknowable, but because we haven't yet developed the senses or instruments necessary to perceive them? Consider how our perception of reality has changed throughout history. Before the microscope, the world of microorganisms was as invisible as dark matter is today. Before telescopes, distant galaxies were inconceivable mysteries. Before radiation detectors, electromagnetic waves permeated our world without our awareness of them. Each expansion of our perceptual capacity revealed entire universes that were always there, but were invisible to us. Dark matter may be just the latest of these discoveries, a lesson in humility about how limited our direct perception really is. But there's also an almost mystical beauty in this invisibility. Dark matter connects us to ancient spiritual traditions that always insisted reality's deepest levels are beyond the senses. I'm not suggesting that modern physics validates specific religious beliefs, but there's a poetic resonance between discovering a cosmos dominated by the invisible and mystical intuitions that the most important things often can't be seen. In many contemplative traditions, there's the idea that our common perception shows us only reality's surface. Meditation, prayer, contemplation are practices designed to tune us into existence's deeper dimensions. Dark matter suggests that, at least on the cosmological level, this intuition may be correct. The universe's visible surface is only a small fraction of a much vaster reality. This also raises questions about consciousness and perception. If there are forms of matter that are fundamentally invisible to us, could there be forms of consciousness equally invisible? Are we alone in a vast universe, or just blind to companions who may be everywhere around us? I'm not suggesting that dark matter is conscious. There's no evidence for that. But discovering that most of reality is invisible to us opens conceptual possibilities that previously seemed purely speculative. If matter can exist in forms we never imagined, what other forms of organization, complexity, even experience might exist in dimensions we haven't learned to perceive? Dark matter also teaches us something profound about the relationship between knowledge and mystery. On one hand, it represents one of modern science's greatest mysteries. On the other hand, paradoxically, its discovery has enormously expanded our knowledge of the universe. We now know we live in a cosmos much richer, more complex, and more mysterious than we imagined. It's as if each answer we find reveals even deeper and more profound questions. And perhaps that's exactly how it should be. Perhaps the purpose of scientific pursuit isn't to eliminate all mystery, but to lead us to increasingly deeper and more wonderful mysteries. Dark matter reminds us that we are explorers in a universe whose vastness and strangeness far exceed our current capacity for understanding. And there's something profoundly humbling and inspiring in this realization. We are small, our perception is limited, our knowledge is incomplete, and yet we're capable of detecting our own ignorance and working to expand it. Have you ever wondered if this capacity to know our own ignorance might be one of consciousness's most remarkable characteristics? That we're apparently unique in the known universe for our ability to contemplate not just what we know, but the vast ocean of what we don't know. In these final moments of our journey together, I want you to breathe deeply and feel the silent weight of existence around you. With each breath, trillions of dark matter particles are passing through your body, carrying with them echoes of 13.8 billion years of cosmic history. They were there when the first stars ignited their nuclear furnaces. They witnessed the birth and death of countless suns. And they'll be here long after our own star becomes a cold white dwarf. There's something deeply comforting in this cosmic perspective. No matter what challenges you're facing in your personal life, no matter how isolated or lost you might feel sometimes, you are literally immersed in an ancient and eternal presence. Dark matter is like an invisible cosmic embrace, connecting you not just to the present, but to the entire history of the universe. Imagine for a moment that you could see dark matter. The world would transform into a visual symphony of invisible structures, giant filaments of matter connecting galaxies like a cosmic neural network, bright halos enveloping every star, streams of particles flowing through intergalactic space like rivers of ghostly light. You would see that you're not just walking on a rocky planet orbiting an ordinary star, but navigating through an invisible architecture as complex and beautiful as any cathedral ever built. Dark matter would be like seeing music, patterns of pure beauty that were always there, but that your senses could never capture. And perhaps that's exactly what science does for us. It gives us eyes to see the invisible, ears to hear the inaudible, minds to understand the incomprehensible. Through the instruments of physics and astronomy, we develop senses that transcend the biological limitations of our evolution. But dark matter's deepest lesson might be about acceptance and humility. We live in a universe where 95% of reality is mysterious. This can make us anxious. After all, we like to feel we understand our place in the world. Or it can fill us with wonder and gratitude for being part of something so vast and mysterious. Choose wonder. Choose curiosity. Choose the joyful humility of knowing you're part of a cosmic story so rich and complex that a single human life can barely scratch its surface. Dark matter teaches us that the deepest mysteries often hide in plain sight. For decades, astronomers observed galaxies without realizing they were seeing only the tip of the iceberg. Most of reality was there, influencing every observation but remaining completely invisible. How many other mysteries are hidden in plain sight in our own lives? How many forms of beauty, meaning, and connection do we pass by every day without noticing? The search for dark matter is also a metaphor for the search for all the invisible dimensions of human experience. Perhaps the true discovery isn't just what the universe is made of, but how to expand our capacity for perception, our openness to mystery, our willingness to live comfortably with questions that may not have simple answers. Dark matter whispers to us that reality is much stranger, vaster, and more beautiful than our everyday experience suggests. And this whisper continues, night after night, while galaxies dance their silent gravitational dances, while invisible particles cross the cosmos, while space-time itself expands, carrying with it the secrets of its own origin. You are part of this story. Every atom in your body was forged in a star's heart that could only exist because dark matter created the necessary gravitational conditions. You are made of stardust, shaped by invisible forces, participating in a cosmic drama that began before time had meaning. And now, in this quiet moment, you can choose how to relate to this mystery. You can feel small and insignificant, or you can feel profoundly connected to the cosmos's grandeur. You can be frustrated by what we don't know, or you can marvel at the fact that we're capable of asking these questions. Dark matter is there, around you, through you, part of you, connecting you to everything that ever existed and everything that will exist. It's eternity's whisper, reminding us that we are temporary participants in a story much larger than ourselves. And perhaps that's enough for now to simply listen to that whisper with gratitude and wonder. And so we come to the end of our journey together, but also, paradoxically, to its true beginning. Because now that you know dark matter, not just as a scientific concept, but as an invisible presence that permeates every moment of your existence, you'll never look at the universe the same way again. When you go out tonight and look at the stars, remember that each point of light you see is enveloped by a halo 5 times more massive than matter your eyes will never be able to detect. When you feel the night breeze on your face, know that trillions of particles of a completely different type are flowing through you at that same moment, carrying information from epochs when the universe was young. Dark matter has transformed our understanding of the cosmos. But perhaps its most important lesson is about how to approach the unknown. In a universe where 95% of reality remains mysterious, the only sensible attitude is a mixture of rigorous scientific curiosity and profound humility. We thought we were the protagonists of the cosmic story, made of the universe's main substance. We discovered we're a minority, perhaps even a curiosity in a cosmos, dominated by forms of matter and energy we've barely begun to understand. And yet here we are, capable of detecting our own ignorance, of asking questions about our own insignificance, of building instruments that reveal the vastness of what we don't know. There's an almost absurd beauty in this. We're like children playing on the beach of infinity, occasionally finding a shell more beautiful than others, while the entire ocean of mystery stretches before us. And perhaps that's exactly how it should be. Science didn't promise us certainty, it promised us adventure. And what an adventure we have ahead. Increasingly sensitive detectors being built underground. Increasingly powerful telescopes probing the edges of space-time. Increasingly bold theories trying to connect the very small with the very large. Increasingly sophisticated computer simulations recreating the evolution of entire universes. Perhaps tomorrow, while you work or rest, an underground detector will finally capture the first unequivocal dark matter particle. Perhaps in the next decade, space telescopes will reveal structures in the cosmic background radiation that finally tell us what the dark sector is made of. Or perhaps the answer is so strange we'll need to develop completely new concepts to understand it. Any of these possibilities would be fascinating. But there's also a possibility that might be the most beautiful of all, that dark matter will always remain a partial mystery, always reminding us that we live in a universe much larger and stranger than our capacity for complete understanding. Because perhaps it's mystery, not resolution, that keeps us human. It's the capacity to ask questions without easy answers, to live comfortably with uncertainty, to find beauty in the incomprehensible that distinguishes us as a conscious species. Dark matter teaches us that the universe is generous with its mysteries. For every question we answer, it offers us 10 new questions even more profound. For every veil we lift, we discover 3 other veils behind it. It's a special kind of abundance, an abundance of wonder. And you, dear listener, are now part of this search. You don't need to be a physicist or astronomer. You just need to carry with you the awareness that you live immersed in mystery, that every moment of your life happens against the backdrop of a cosmic story of unimaginable complexity and beauty. When you face difficulties in your personal life, remember you're part of a much larger story. When you feel lost or alone, remember you're literally surrounded by a cosmic presence that connects you to everything that exists. When you feel tempted by arrogance or excessive certainty, remember you live in a universe where 95% of reality remains mysterious. Dark matter is the ultimate humility teacher. It's everywhere, fundamental to our existence, and yet remains forever beyond our direct perception. It's like having an invisible guardian angel that never reveals itself, but whose presence sustains every moment of our existence. Thank you for accompanying me on this journey through the invisible. Thank you for your patience with mysteries, your openness to possibilities, your willingness to contemplate questions that may not have simple answers. It's through explorers like you that our species continues expanding the frontiers of knowledge and wonder. Dark matter is there now, as you listen to me, flowing through you like a silent current connecting you to the entire cosmos. It will be there when you fall asleep tonight, when you wake tomorrow, when you continue your own journey through this mysterious and precious life. And perhaps, in the end, that's the most important discovery of all. That we are part of something infinitely larger than ourselves, something we'll never completely understand, but in which we can participate with gratitude, curiosity, and wonder. If you could ask dark matter one question, this invisible presence that shaped the cosmos's destiny and made your existence possible, what would you ask? And might you, in the deep silence that would follow, be able to hear something like an answer?